Earth is quietly dragging a tail through space, and almost nobody ever sees it. It isn't a gas tail like a comet. It's magnetic, and it begins with the invisible shield that surrounds our planet, the magnetosphere. The sun constantly releases a stream of charged particles called the solar wind. When that solar wind reaches Earth, it pushes directly against our magnetic field. On the side facing the sun, that pressure compresses the field and squeezes the magnetosphere closer to the planet. But on the opposite side, the night side, the field is pulled outward and stretched into a long, invisible extension. That stretched region is Earth's magnetotail. The magnetotail is not a fixed-length object. It breathes and shifts as solar wind conditions change. When the solar wind is stronger or when the magnetic field is disturbed, the tail can extend dramatically, reaching far beyond the moon's orbit and stretching millions of kilometers downstream. So the first idea is simple, but hard to visualize. Earth's magnetic field doesn't stop near the planet. It forms a huge, downwind structure shaped by the sun, like a windsock in space. But the magnetotail isn't a single smooth tube, and it isn't empty. It has structure. If you could see it, you would notice two large magnetic lobes, one above and one below a central layer. Between those lobes lies a region called the plasma sheet. In the lobes, the magnetic field is stronger and the particle density is lower. In the plasma sheet, the magnetic field is weaker and the particle density is higher. That central sheet is important because it's where a lot of the action happens. This structure matters because the magnetotail behaves like an energy storage system. The solar wind doesn't just blow past Earth. It can transfer energy into Earth's magnetic field. Over time, that energy loads into the stretched tail, like tension building in a pulled rubber band. The magnetotail is the stretched part of that rubber band, the part most likely to rearrange suddenly. And we don't know this only because it makes sense in models. We know it because spacecraft have flown through it. NASA's Themis mission deployed multiple satellites to study Earth's magnetosphere and to understand what triggers sudden disturbances called substorms. Two of those spacecraft were later repositioned near the Moon as part of the Artemis mission, which makes them especially useful for measuring magnetic conditions at lunar distances, right where the magnetotail can reach. Those satellites measured real changes in magnetic fields, particle populations, and energy flow. In other words, the magnetotail is not an abstract concept. It's a physical region that instruments can sample directly. Now here's where the tail becomes more than a curiosity. Sometimes the magnetotail releases stored energy rapidly. One of the main ways it does this is through a process called magnetic reconnection. Magnetic reconnection happens when magnetic field lines are forced into a stressed configuration and then suddenly break and reconnect into a new pattern. When that happens, energy that was stored in the magnetic field is converted into motion and heat and accelerated particles. Think of it like this: the magnetotail is a stretched system under constant pressure from the solar wind. Reconnection is the moment the stretched configuration reorganizes, and that reorganization can release a burst of energy. This is directly tied to substorms. Substorms are rapid disturbances in Earth's magnetosphere that can cause the aurora to brighten suddenly and expand across the sky. The key point is that auroras are not just pretty lights. They're evidence that energetic particles are being guided down magnetic field lines into Earth's upper atmosphere. When those particles collide with oxygen and nitrogen high above the surface, the atmosphere emits light. That's what you're seeing in an aurora, a visible footprint of invisible space physics. So when you see the northern lights intensify suddenly, you may be watching the result of energy being released far down Earth's magnetic tail and then funneled toward the polar regions. This is also why space weather is treated like a real operational risk, not a fun trivia fact. Space weather agencies track geomagnetic activity because disturbances in Earth's magnetic field can affect systems we depend on. Strong geomagnetic storms can interfere with high-frequency radio communication, disturb satellite navigation signals like GPS, and in some cases drive currents that matter to electrical power transmission systems. That does not mean your phone will explode every time the aurora shows up. It means Earth's space environment is an active system that can couple into technology, and the magnetotail is part of the mechanism that stores and releases energy. Now let's go back to scale, because this is where most intuition fails. Earth's atmosphere ends a few hundred kilometers up, but Earth's magnetic environment extends vastly farther. The Moon orbits at about 60 Earth radii from the planet. Under the right conditions, the magnetotail can stretch well beyond that distance. That means the Moon can pass through regions shaped by Earth's magnetosphere. This does not mean the Moon is inside Earth's atmosphere. It means Earth's magnetic influence, under pressure from the solar wind, can reach astonishing distances into space. So if you imagine Earth as just a small sphere surrounded by a tiny bubble, that mental model is wrong. The magnetosphere is huge, and the magnetotail is the downwind extension of that system. Now here's the part most people miss. Even when nothing dramatic happens on Earth, the magnetotail is still moving. It shifts in thickness, it flaps, it changes orientation, it stretches and relaxes, it stores energy and sometimes releases it. It's a living space weather structure shaped by an ongoing interaction between the Sun and Earth's magnetic field. So the clean takeaway is this. The solar wind compresses Earth's magnetic field on the day side and stretches it into a long magnetotail on the night side. That tail has structure, lobes and a plasma sheet. It can store energy from the solar wind, and when reconnection releases that energy, it can drive substorms that intensify auroras and contribute to space weather effects that matter to satellites, navigation, and communications. Which brings us back to the simplest statement from Monday's short. Earth has a tail in space. You can't see it with your eyes, but satellites can measure it, and the night sky can show you what it's doing. And on Thursday, we'll go one step deeper. The snap moment. What magnetic reconnection actually looks like in the magnetotail, and why it can turn stored energy into a sudden auroral surge. You live on a planet with a space tail, and it's moving right now.